Hello and welcome. In this video, I will show how I transformed a standard bathroom scale into a talking scale for visually impaired users. The original load sensors and mechanics were reused, while the electronics were replaced with a custom ESP32S3 based design. The finished device announces the measured weight through a loudspeaker, supports battery or USB operation, and can be configured wirelessly. All hardware and software will be released as open source. Let's start with a quick demonstration.
159.0 pounds. 159.0 pounds.
Before starting the hardware design, I defined a set of goals and requirements for the project. The main objective was to create a practical and accessible bathroom scale for visually impaired users while keeping the design simple, affordable, and easy to reproduce. I also wanted to reuse an existing commercial scale, providing a convenient wireless configuration interface and achieve long battery life without sacrificing usability. Finally, all hardware, firmware, and mechanical designs should be released as open source, allowing others to build upon the project and adapt it to their own needs. To reuse the mechanics of the original scale, I first needed to understand how the weight sensors work. The scale contains 4 identical load sensors, one in each corner. Each sensor forms a half bridge consisting of 2 strain gauges whose resistance changes slightly when force is applied. The 4 half bridges are connected to form a Wheatstone bridge. The wiring is arranged so that the resistance changes add up, maximizing the output signal. A supply voltage is applied across the bridge, while a differential voltage is measured between its 2 output nodes. Without any load, the bridge is balanced and the output is close to zero. When someone steps onto the scale, the bridge becomes slightly unbalanced, producing a small voltage proportional to the applied weight. On the right side, you can see the disassembled scale with the 4 load sensors and the wiring. This block diagram shows the overall architecture of the talking bathroom scale. The Wheatstone bridge generates a small differential signal proportional to the applied weight. This signal is amplified and digitized by the HX711 and then processed by the ESP32S3 microcontroller. For the voice announcement, the ESP32 sends digital audio data to the MAX98357A audio amplifier, which drives the loudspeaker. The lower part of the diagram shows the power supply. 3 AAA batteries feed a TPS62740 buck converter, providing a regulated 3.3 volt supply. A P-channel MOSFET allows the ESP32 to switch power for the load cell bridge and audio amplifier. Since these are among the largest power consumers, disconnecting them during deep sleep significantly reduces energy consumption. As a result, the scale can achieve very long battery life while remaining ready to immediate use. This slide shows the complete hardware installed inside the original scale housing. One of the design goals was to reuse as much of the existing mechanical structure as possible. Instead of modifying the enclosure itself, all new components are mounted on a custom 3D printed carrier that fits into the available space inside the scale. On the left side, you can see the loudspeaker used for the voice announcements. The model was chosen to provide high volume while making efficient use of the available space. In the center is the custom-designed printed circuit board. This board contains all the electronics required for the project, including the ESP32S3 microcontroller, the HX711 load cell ADC, and the MAX98357A audio amplifier, and the TPS 62740 power supply. On the right side, the 3D printed carrier integrates a battery compartment for three AAA cells. This provides a compact and reliable power source while keeping battery replacement simple for the user. The result is a clean, mechanically robust assembly that fits entirely within the original scale enclosure. From the outside, the scale looks almost unchanged, while internally it has transformed into a fully voice-enabled device with wireless configuration and long battery life. The firmware supports two operating modes, normal operation and configuration mode. During normal operation, the ESP32 spends most of its time in deep sleep. It periodically wakes up, performs a quick weight check, and immediately returns to sleep if no person is detected. When the measured weight exceeds a configurable threshold, a full measurement is performed and the result is announced through the loudspeaker. The configuration mode is entered by pressing the configuration button. The ESP32 starts a Wi-Fi access point and provides a captive portal that can be accessed from a smartphone, tablet, or a computer. Using the web interface, the user can adjust settings such as the weight unit, language, and calibration parameters. Once the configuration is complete, the device is restarted and returns to normal operation. Power consumption was an important design goal because the scale is intended to run from three AAA batteries. To minimize energy usage, the ESP32 spends most of its time in deep sleep. The HX711 is placed into power down mode, and both the load cell bridge and the audio amplifier are completely disconnected using a switched power rail. As a result, the measured sleep current is only 7 microamps. Every few seconds, the system wakes up briefly to check whether someone is standing on the scale. This wake-up phase consumes about 25 milliamps for only 80 milliseconds. Based on these measurements, the expected battery life ranges from about 1 year to almost 3 years, depending on the selected wake-up interval. Well, here are my conclusions. In this project, I transformed a standard bathroom scale into a talking scale designed for visually impaired users. By reusing the existing mechanics and load sensors, only the electronics needed to be replaced, resulting in a cost-effective and practical solution. The ESP32S3 platform provides both the processing power for the voice announcements and a convenient wireless configuration interface through a captive portal. Special attention was given to power consumption, allowing the device to operate for extended periods from just three AAA batteries. All hardware design files, firmware, source code, and 3D print models will be released as open source, making it easy for others to build, modify, and improve the design. Thank you for watching, and I hope this project inspires you to create more accessible devices.